thank you for the opportunity to speak here in this distinguished series of seminar talks. So today I would like to tell you about how to connect electrical impedance tomography and X-ray tomography in a quite exciting way, at least in my opinion. Let's see what you think. So first, let me still mention that I represent the Finnish Center of Excellence in Inverse Modeling and Imaging, our network of inversion covering the map of Finland. Also, I would invite you to visit my YouTube channel with fun science. And also, let me point out, we started recently a new channel in YouTube called Inverse Problems channel. So there is, for example, EIT 101, very basic introduction, and then there is an inverse scattering video, Fioral band I made. So I warmly welcome you to enjoy science videos. Okay, so today's topic, first of all, let me remind you of the most classical inverse problem of all. We have an unknown object there under the question mark, and the only thing we know, we can measure the X-ray attenuations, take a logarithm, and then we see how much attenuating stuff is there in the way of each X-ray. And of course, the most classical way to treat the data is to use filtered back projection and find what is there, in this case, a human head. So we get a slice image. Of course, this is really the very basics of inverse problems. Then, of course, another basic problem is electrical impedance tomography. Here I'm showing it in a context of trigonometric current patterns fed into this beautiful phantom built by John Newell at RPI. So currents are fed. Then there are many ways of making an image. One of the nonlinear ways is based on Adrian Nachman's proof of the two-dimensional inverse conductivity problem and added with some regularization steps and implemented, so we get an image like this. So there are two very basic classical inverse problems. The X-ray one being mildly ill-posed in that full angle case, and EIT being nonlinear and extremely ill-posed. And of course, X-ray tomography is a linear inverse problem. So let's see how we could connect those two. To fix notation and to go through the basics of EIT, let me just show you this slide. I'm working today in dimension 2 in the unit disk, actually, although the stuff here can be done in more general 2D domains as well. And I'm taking, assuming that sigma is the conductivity function bounded from below, bounded away from 0, and also bounded from above. And then we look at the conductivity equation, the Dirichlet problem, where there is a voltage Beltrami style complex geometric optic solutions. So we just switch from sigma to mu with this nonlinear but very simple transformation that can be used back and forth. So we can easily go between sigma and mu in a very easy way. Then let's consider taking the radon transform of mu. This is mildly ill-posed. I think there should be ill-posed, but it's missing. So this is a mildly ill-posed problem going back from if we know the radon transform of mu. So parallel beam, very basic radon transform, and its inverse. Then consider taking a vertical derivative of the sinogram. So differentiating along the one-dimensional dimension, so not the angle, but the linear dimension in the sinogram. And we can also get back from this sinogram if we want by just taking the integral up to x and then finding back the sinogram. Then I can add a complex phase factor, just multiplying with a complex valued function depending on the angle in the sinogram. So there's really no extra information in this step, just the same information in a complex form. This one, in turn, we can consider convolving along the linear dimension. So there's a blur operation applied separately or independently into each vertical line in this complex sinogram. And there, in principle, we can go backwards by deep blurring, but of course that will be very ill-posed, although it's a linear inverse problem, but very ill-posed. Okay, well, there's a sequence of stuff here. Why would anyone do something like this? Well, the reason is that actually we can calculate this blurred complex sinogram from EIT data. Almost, but very closely. So actually, this is a new way of looking at EIT, kind of dividing up the EIT reconstruction problem in a different kind of steps than usual. What I like about this approach is that we can compartmentalize ill-posedness quite nicely. It will be here, a little bit of ill-posedness here in the classical filtered back projection, then a lot of ill-posedness in the deblurring, but also it's quite restricted in the way that the deblur happens independently in each vertical line. And also we have a very clear geometric understanding of each of the data points here, because it really boils down to the classical sinogram. So this gives a new geometric view of how we use the EIT measurement information. So how on earth would something like this be possible? Well, it's based on complex geometric optic solutions of the Beltrami kind, then a specific one-dimensional Fourier transform trick that brings us to the beautiful world of complex principal type operators, which we will explore a little bit next. But anyway, let me just quick show you then the blurred complex data looks like this. The yellow is the real part, magenta is the imaginary part. So the information about the conductivity is in this kind of form, and what you see in the middle is not the conductivity, it's the mu function. And then of course we could do a filtered back projection reconstruction that would give us a very blurred image, which is of course not much better than any old EIT method. Although here there's a possibility of looking at the regularization in the way that now the regularization would mean deconvolving each of these 1D profiles and then applying filtered back projection. So that would be kind of a new way of looking at this problem. Okay. So such a diagram of steps, let's see where they come from. This work has been done together with Alan Greenleaf, Matti Lassas, Matteo Santacesaria, and Günther Uhlmann. Actually, this has been quite a long project. I think we started working on this in 1999 or something like that, and got the paper out in 2018. It was quite a journey to find these things. So the final construction we published is based on these Beltrami-type CGO solutions constructed by Kari Astala and Lassi Päivärinta, published in 2006. So the first step is really going from the conductivity sigma to this coefficient mu. This mu coefficient is in absolute value, it's less than 1. And it's put here into the Beltrami equation as a real valued multiplier function. So we have here the d bar operator, which is this one, that gives 0 to complex analytic functions. And we have the D operator here under the complex conjugation. And here, what's nice about this solution F of the Beltrami equation, that the real part is a solution of the conductivity equation with sigma, and imaginary part is the solution of the conductivity equation with 1 over sigma. It's curious that actually we can calculate the traces of these CGO solutions from the measurements from the DN map of sigma only, so we can also find the CGO solutions for 1 over sigma. So these CGO solutions have the following form. So there is the typical e to the ikz, and ikz here is an exponentially growing and decaying and oscillating function. So it's not unitary function, but it has complex multiplication in this notation. And then we have here, I call it omega plus for mu and omega minus for minus mu, because sigma corresponds to 1 over sigma, the same way mu corresponds to minus mu. And there's an asymptotic like radiation condition for the remainder part omega plus minus, like this. So these are the solutions we are working with. For the CGO solutions were started in 1987 in our field by Sylvester and Ullman, and these Beltrami-type solutions have this kind of history. They were constructed in 2006, and then numerically, this is kind of a numerical history. We first evaluated the solutions in this paper. Then we actually built a kind of reconstruction method, like a numerical implementation of the Astala-Päivärinta approach, so to speak. And then Huhtanen and Perämäki, actually even before we already used these methods in this paper, they published a really powerful numerical method for calculating these solutions. And then also we analyzed some Gibbs phenomenon type of thing with this nonlinear exponential in this paper. All right, and then the trick from the 2018 paper is to apply a one-dimensional Fourier transform by writing the complex spectral parameter K in polar form like this, or not quite polar form because tau here is in R. So tau is not only positive, but it's really in whole of R. So we define omega hat plus and also omega hat minus in this way. We separate this tau and e to the I phi parts of the complex number, and we take the Fourier transform with respect to tau, and then we get this omega hat, where we call this Fourier parameter, Fourier variable, we call it pseudo time. So we just do this one-dimensional trick, and then actually the underlying theory of complex principal type operators leads to very interesting ways of singularity propagation. We'll see a little example of that a bit later, but let me first describe to you how we can actually write these solutions, CGO solutions, as a scattering series, not physical scattering, but a mathematical formal scattering series. And we make heavy use of this Huhtanen and Perämäki revised or modified construction of the Astala-Päivärinta solutions. For that, we need the Cauchy transform, the inverse of d bar, and the Berling transform that can switch between the d and d bar derivatives, defined by these formulas here, Cauchy principal type integral. Then we take this EKZ, which is just an oscillatory unitary exponential. Then alpha contains the E minus k, z, and then some multiplication with minus ik bar, and then mu here, the Beltrami coefficient. And nu is just the Beltrami coefficient multiplied by this one. And we use the operator A that has the Cauchy transform, Berling transform, and pointwise multiplications with the conjugates of these alpha and nu functions. And the scattering series works like this. We write the omega solutions in an infinite series like this, where the first term, omega 1, is very simple. Omega 1 is just minus d bar inverse applied to u1 conjugate, where u1 actually is just minus alpha bar. And then recursively, we can go on and construct all of these terms in this series, and in a formal way, in a mathematical way, these correspond to first scattering and multiple scattering solutions. And then we can prove a theorem. Like in microlocal analysis, there are these generalized situations where filtered back projection type formulas can be derived. And such a formula also applies to our case. So if we define this kind of averaging operator, T1 plus and minus, so we integrate over the boundary of the unit disk. So this is over the boundary of the domain where we do EIT. So we integrate away the z variable in the CGO solutions, or actually the Fourier transforms of the CGO solutions. So we lose the z, we average over z, so the pseudo time and the direction is only remaining. And then actually, if we are given T1 plus or minus mu, we can recover mu by applying the adjoint or the back projection operator in a generalized sense, and then applying this kind of filter. So this is very similar to the classical filtered back projection for the radon transform. So formally, it looks pretty much the same, except that here we have a plus exponent. So here is a roughening operator, and here we have a smoothing operator. So there's a little difference there. But let me offer you a different view of this formula. Namely, we can write T1 plus, well, the heroic effort of Alan Greenleaf writing this down. I truly admire this achievement, writing it down in this way, containing the classical radon transform of mu here in the heart of the formula. Here we see the ds. So, well, here is mu, here is r mu. So we go from mu to r mu, that's the sinogram. Then we differentiate the sinogram with respect to s. That's here, the derivative of the sinogram. Then we multiply by this complex phase factor, depending only on phi. So then we get this complex sinogram we already saw before. That's T1 plus of mu. So going all the way back from T1 plus mu to the conductivity is rather easy. There's algebra, explicit integral, mildly ill-posed FBP, and then just a nonlinear algebra, but very simple. But of course, this is not the full story of EIT. We know EIT is very ill-posed. It has to be somewhere. So let's work our way towards EIT data. So the first thing is to apply convolution. Let me just take, let's say, a Gaussian kernel I call G, and I convolve each of these profile functions. Real and imaginary parts both are convolved, so they become much smoother and they spread out. So that's the next step in our diagram. And of course, now this linear deblurring problem is very ill-posed. And still we don't see the EIT data. We should be able to go from the DN map to this blurred sinogram. I put here a wiggly arrow because I'm cheating a little bit because the terms, scattering terms are ignored. Let's see how this works. So first of all, let me point out that we can solve for the traces of the CGO solutions from the DN map. This is explained in a paper by Kari and Lassi in 2006 as well, a different paper, not their annals paper, but another paper. They explain how this boundary integral equation works. And now how the ill-posedness of EIT shows up is that when we calculate, when we solve for the traces of omega plus or minus from that boundary integral equation, the bigger tau we want to use, so the complex parameter more far away from the origin in the complex plane, we see that the measurement noise will cause more and more errors. Bigger errors, the more far away we are from the origin. So for low noise, we have this quite wide interval of OK accuracy, but with higher noise, we need to restrict closer to the origin to get reliable noise robust inversions or calculations of the point values of these CGO solutions. But if we restrict into this OK accuracy area, then we have a noise robust calculation. Okay, then. So let me now define not omega hat, but omega whatever this is, kind of omega hat inverse that involves a window in the Fourier transform. So it's kind of a classical engineering trick, of course. If we don't have the high frequencies reliably, let's cut them out. So I'm using here a Gaussian window and a hard cutoff, but let's think that this cutoff is done, or we choose the width of this Gaussian so that the Gaussian is very small at minus r and r. So this is a windowed Fourier transform of the CGO solutions instead of the strict full Fourier transform. And now we did consider the blurred T1 plus minus. When we put the blur inside the definition, we can push it to the Fourier side. So we can think that, okay, the blurred side comes from windowed Fourier transform omega 1. And then we ignore the higher order terms, or actually when we compute from the DN map, it's this one we can compute. It contains all the scattering, all the higher order scattering thingies are involved, but our filtered back projection theorem concerns this omega 1 guy that only has the first order scattering. So that's why here is only approximate equality, but it's close. So we can compute something that's very close to this whole diagram here. That's behind this whole approach. So this is now the diagram, and we are doing this little wiggly cheating here. So how bad is this cheating really? Let's take a look at one specific example, a very simple conductivity being 1 near the boundary and jumping up to 10 in the disk of radius 0.2. So I'm fixing Z to be 1 in the complex plane and K, complex K parameters actually range on the real axis. In this case, we have this kind of propagation of singularities along two-dimensional leaves because we are dealing with a complex principal type operators. So we have singularities propagating in this unusual manner. And for the example, if I cut this, so in this picture, the vertical dimension is the pseudo time t. And let me cut this picture in the sagittal way. Anyway, I'll cut this. Well, I don't know how to explain it, but anyway, we are looking that image on a vertical cut. So we see the slanted plane, that was the magenta plane, it's here. When the magenta plane hits, so here's the where the conductivity jumps. This one, so plus 0.2 and minus 0.2. When the slanted plane hits here at the right wavefront set direction, it creates another vertical horizontal plane of simulation here and also here. They will contribute very strongly to this first order scattering. I'm subtracting these two guys because then we get rid of all the even scatterings. They will just cancel. So we only have the odd terms to worry about. So T1 is the major one. We see the jumps of conductivity very strongly there. And that's what our filtered back projection theorem is concerning. So we see the main information in the first order scattering. Then there is potential trouble coming from the higher order terms. At present, there is no theoretical result telling how significant the higher order terms are. But numerically, for example, here we can see that they are much smaller than the first order scattering. And in all the numerical tests, the higher order terms seem to be negligible. There is no real trouble with that. And here we can see they are rather small. Well, this is of course not a proof, but anyway, an indication that or kind of evidence for this method. Okay, so that was kind of the theoretical background. There's a lot to do in that area as well, but today I would like to explain a little bit how we try to apply this whole machinery to the medical application of stroke classification and monitoring. So here the idea would be that strokes in the classification problem, there either is too little blood because there's an ischemic stroke like this, or there is too much blood like we see here. The symptoms are the same. Could we use EIT to see which is which? It's kind of promising because different tissues inside the head do differ in electric conductivity properties. So maybe we could have a device, something like this, to see what's going on inside the head. Another application would be monitoring in the bedside. Currently, patients like this need to be taken to CT, really physically transported from here to the CT. And that this is, of course, not good for a very sick patient. So with EIT, we monitor on bedside even for over several days without any known harm. Okay, we have a big project going on, lots of collaborators there. And let me explain a little bit how we want to use these virtual hybrid edge detection profiles in this work. So this is work done with Juan Pablo Agnelli, Ainur Chöl, Matti Lassas, Rasmi Murti, and Matteo Santacesaria. And here, well, if we had very accurate, very accurate EIT measurements, then our windowed Fourier transform could have a very wide window and the convolution would not be that bad. So this is totally unrealistic. One could never do these pictures with measured EIT data, but of course we can simulate it. So here we have an ischemic stroke, of course a digital phantom, and here hemorrhage. Now if we compare these profiles, we can see where what's happening inside the head, and maybe we can make the classification. However, when we need to do the windowing, actually in practice, the EIT measurement noise is so high that we have to window very severely. So usually R is 4 or 4.5, where we have to do the frequency cutoff. So the profiles are very blurred like this. So it might not be the best idea to try to recover the whole image, even with deconvolution or all that. Maybe it's better just to use machine learning to dig out the information, because anyway, we are in the stroke application, we are not after the full EIT image. We are actually after the knowledge, which kind of stroke is it in the classification problem. And in the monitoring problem, we have a CT image. We know what the situation is in the beginning. And then we would use EIT to see whether the bleeding is getting worse or better, or whether there is developing hemorrhage around an ischemic stroke. So both of these applications have restricted problem with the full image. We just need some partial information. So maybe we could get it by learning from the VHED profiles. Of course, we could maybe get it from learning from directly from EIT data, but the research hypothesis in this study is that it's better to use nonlinear math, our regularized, robust inverse problems math that has been developed during the last 40 years or so, to pre-process the data, to compute noise-robust nonlinear features and learn from them, and not try to naively learn directly from the raw data. Okay, so let's see what can we say about this situation. So we did produce a lot of random digital phantoms. For training, we use these disks inside the brain, either ischemic low conductivity or hemorrhage high conductivity. And for testing, we tested both with elliptical single inclusions and then also like multiple inclusions that may or may not overlap, and see whether the learning can be generalized from disks to these more general shapes. We tried convolutional neural networks for the Dirichlet-Neumann matrix input. This is the architecture for that. And also we compared convolutional neural networks for VHED profile input to see whether these noise-robust nonlinear features help the learning or not. Okay, what we saw with these irregular inclusions is that it seems to be a better idea to do first some nonlinear math before learning. We get a much better classification rate with the VHED profiles. And same goes with the multiple inclusions. It does generalize. However, these classification rates are not acceptable. I mean, too many patients would be misclassified with this kind of accuracy. So this is not really so good. So we also, the very basic fully connected neural networks. I know these come from the 60s or something like that, but still we compared, and rather surprisingly, we saw that actually these perform quite well for this problem. For irregular inclusions and with different noise levels, we got quite good results, but very good with the VHED. And then for the multiple inclusions, the DN matrix approach failed. See that here for the irregular ones, it was quite okay, but for some reason, the performance dropped very much when there were several components, whereas the fully connected networks could deal quite nicely with the multiple inclusions. But then recently, Rashmi Murthy, a postdoc in my group in Helsinki, tried out these recurrent neural networks as well, and she found that they work even better. So this didn't make it to our paper. These are very new results. So Rashmi just recently computed these and got very good classifications for the irregular ones and also for the multiple inclusions. So our current view on this problem is that these RNNs offer the best architecture for this kind of classification task. Okay, so what to think of all of this? It seems that at least in this application and in a couple of others I've looked at, it seems that even in the era of machine learning, our beloved nonlinear PDE inversion math is extremely useful because we can do a regularized noise robust first step, a nonlinear one tailored to the problem at hand to pre-process the data in a much more understandable format for machine learning. We saw that in this study very clearly. Also, we saw that RNN seems to be better than the other options. And then I am painfully aware that working with two-dimensional disk that are is nearly enough to treat real patients. So our next steps will be generalizing this to realistic head shapes and testing whether this inherently two-dimensional methodology will work if we have a band of electrodes around the head. So the data comes from a 3D structure, but if we still apply this two-dimensional framework, will the learning generalize or not? We'll see. That will be the next step in the study. And this is my time to thank you very much for coming to the talk. And if you have questions, I'm very happy to answer them.
Thank you very much, Samuli, for the great talk. Thank you very much. Are there any questions or comments, please? Please unmute yourself. Are there any questions or comments?
So, hi, Samuli. That was a great talk. So let me ask one question. So when you are using the neural network, so you are classifying between two cases.
Yes.
What if you use something even simpler, like support vector machine or something like that? Does it work?
It's a good question. Yeah, I think we did try at some point, and they seem to work in this simple case as well. So right now, I don't have the numbers how well they perform compared to these ones, but at some point we did try them as well.
Yep.
So I think at least for this kind of phantoms, the VHED profiles are reformulating the problem or modifying the problem in a way that's more easily approachable.
Okay, thanks.
Thank you very much. Are there any other questions or comments, please?
Hi, quick question. First, thank you for your talk. The question is, you mentioned it, but could you please elaborate one more time on a high level? The question is, what is the need for the blur and de-blur step?
Yes. Thank you. That's a very crucial question. So, okay, if we take a look at the basic trick in the whole approach is that we are dealing with the complex geometric optic solutions that have this complex parameter. They are parameterized by this complex spectral variable K. And now the trick is to take the one-dimensional Fourier transform over tau, where tau is so we just write K in this form and integrate over tau. And when we do this integration in the theoretical way, I mean, this is the one-dimensional Fourier transform where the integration really goes from -infinity to infinity. And for this one, we have the theoretical machinery, and we know how to connect this one with the Dirichlet-Neumann map. But then when the data is noisy and we solve for those functions from the data, what happens is that, and this happens also in the D-bar method, it's typical for when using this complex geometric optic solutions in practical EIT. What happens is that for small or for the complex parameter near the origin, like in this case, tau being near 0 in some interval centered at 0, there we can numerically calculate the point values of the CGO solutions at the boundary. But if the K parameter is big or away from the origin, then the noise will destroy our computation. So this is an inherent strength in the complex geometric optics approach. It divides the EIT data information into the robust part, which is for K parameters near the origin, and the unstable part, which is the K parameters outside or far away from the origin. That's why so we would like to take the Fourier transform of this function here. But we see, I mean, I'm calculating the function with several realizations of noise in the data, and we see that whatever we get here in this area is totally not reliable at all. So what we do, we take a Gaussian function and we put it as a weight here. So we cut away the bad part and work with the good part. But then what happens is we are windowing the Fourier transform. And as you know from the relationship between Fourier transform and convolution, I mean, if you multiply the function here on the other side of the transform, it means convolution on the other side of the transform. So the situation is that we would like to have this one, but in practice, we only can compute this one. The blurring comes because of the measurement noise in this framework.
Thank you.
Thanks. Thanks for the question. It was really, really central question.
Thank you very much. Are there any other questions or comments, please?
I have a maybe naive question, and you commented on that during your talk. So in the theoretical part, you proved everything for 2 dimensions.
Yeah.
I mean, I wasn't quick enough to see, I mean, in 3 dimensions or something, can one hope for something like this or not?
Yes, one can. The thing is that, okay, let me, where is the, yeah. So this one, yeah. So now what happens in this picture is that here is the circle where the conductivity jumps. So the horizontal plane here is the plane where the conductivity is defined. And the vertical axis is the pseudo time, which is a mathematical construction. And then there are these different planes going around, carrying singularities around. There's an infinite ladder of these planes. But now, since this is the circle where the conductivity jumps, the unit circle is here a little bit outside, because if we just quickly go, so this is the circle where the conductivity jumps. The unit circle is here. So now the horizontal plane here is in the same plane than this picture. So the singularities arising from this jump are transported by the plane to all of the points at the boundary here. So somehow this is such a small dimensional space that everything has been packed very tightly. Now in 3D, let's say we have a conductivity inside the unit ball, and there is some kind of inclusion inside the unit ball in the conductivity. So then there would be a plane tangenting that inclusion ball, and the plane then will intersect the boundary of the domain, the unit sphere, along a circle, but not at every point of the unit sphere, just in a subset, which is a circle. And it turns out that the precise analysis of all these circles running around and going, it's very complicated. So in principle, all of this complex principal type machinery generalizes naturally to the 3D situation, but it's just a really, really complicated mess how everything is intersecting and moving around, and how to integrate over what, and yeah. So it's there, but it's complicated.
But so if I may ask again, so does that also mean that this very nice splitting which you had, I mean, with separating the singularities in this mildly ill-posed bit and the strong ill-posed bit, that is, I mean, not a two-dimensional phenomenon, that you can also do in other dimensions?
Yeah, well, I know that Alan Greenleaf has put a lot of hours into trying to find the similar filtered back projection formula for the 3D case, but so far it's been elusive to find out over what to integrate and how does it. So the research hypothesis is that there is such a thing in 3D, but it has not been found yet.
Thanks a lot.
Thank you.
Thank you very much. Are there any other questions or comments, please? Okay, any other questions or comments? Okay, if not, thank you very much, Samuli, for the great talk. Thank you very much, everyone, for coming. Thank you very much.